Hello everyone, my name is Jack Shaw and I'm the Regional Manager of Europe here at REGENESIS, and thank you for joining us today. Today's presentation will be given by myself and also my colleagues Jim Ford, who is the Technical Manager of the UK and Scandinavia, and Sarah Hughes, who is the District Manager of the UK and Scandinavia. Before we start, I just want to cover off a couple of administrative things. Should you experience any sound or connectivity issues around the webinar, then please end your webinar session, close your browser, and then restart and log back in again. We are recording this, so if you are unable to attend for the entire session, then you can catch up with us on that particular recording. We'll also share that recording with you all in the next couple of days. With regards to questions, if you have any during or after the main presentation, we encourage you to post them using the control panel. I'll collect all of the questions and we'll do our best to answer them at the end of the webinar in a separate Q&A session. And we'll try and keep this webinar, including questions and answers, within an hour. If we don't get to your question, don't worry, we will take it and we will get back to you separately and we'll follow up via email. I'm now going to start the presentation. I will now share my screen and yeah, we'll get going. So give me a second here. Perfect. So yes, the title of this webinar is going to be Mastering In Situ Remediation. And the real goal of this is to ensure that everybody understands, everyone understands the key decisions that we make to ensure that we can deliver an effective design and implementation of these different injectable substrates. So what I'm hoping that you'll see is how we use the site investigation data that you collect, how that then impacts our remediation design process, and then ultimately what that transpires to in the field. REGENESIS as a company, we have been developing and implementing in situ remediation strategies for just over 30 years now, primarily utilizing the injection of substrates into the ground to remediate things like petroleum hydrocarbons or chlorinated solvents, and more recently PFAS. And in about 2011, we started offering an optional turnkey service where we come onto site and do those injection works for you. So using all of this experience, what we have done is pulled a webinar together to highlight the really important bits of information that we need, what gaps we often see in the understanding of a particular site, and how all of this feeds into selecting a particular technology. So none of this presentation is going to be really specifically about one product, but more about the process of coming up with an in situ remediation strategy. So as part of an overview, we're going to take you through a journey of these activities and the decisions that we have to make to design and implement a successful in situ strategy. And as part of this webinar, we're going to look at the site data, why that's important and what and how that impacts our designs. And also this really important step that we often see is missed, where there isn't a remediation design characterization phase, which is basically a site investigation that has been designed to inform a remediation strategy. We'll then link that back to gap analysis and then talk about how we then design and dose the different technologies that we have on offer. And then finally, we will look at field implementation. So how does all of that site investigation data not only feed into the design, but also feed into how we actually undertake these injection works. And then we'll talk a little bit about placement validation as well. And then we'll have that Q&A session towards the end. So broadly speaking, this is our process. So I'm here to talk about the site evaluation phase. I will then be handing over to my colleague Jim, that will talk about the technology selection and remediation design elements. And then finally, Sarah will talk about the product implementation phase. Now, Post-evaluation isn't something that we as a company do. It's pretty unusual for us to be taking samples to verify that our technologies are working. That's always done by a third party. But the sort of samples we do take and the readings that we do take is often around, has our technology been installed correctly? So that's what Sarah will be talking about. So site evaluation. So typically what happens is a consultant or a remediation contractor or an entrepreneur or a liability holder would reach out to us and say, we have a problem with this site. Do you think you can help us? Now, what is typical is maybe a site investigation has been done, a risk assessment has been carried out, and a problem has been identified. The earliest you could get us involved, however, is in the supplementary site investigation phase, and we'll talk about that as we move through this section of the presentation. But when that site first lands on our desk, we have three main questions that we need to ask. The first is, what technology is going to be most appropriate? There's lots of different ways that you can remediate sites that are impacted with petroleum hydrocarbons and chlorinated solvents. So which is the most appropriate technology that we can reach for? And also, can we even help? We're very comfortable about saying no if we don't think that our solution is appropriate for your site. So we will highlight that pretty early on in this process if we don't think that we're going to be able to help you guys out. The second thing is, how are we going to get these substrates into the ground? Should we inject them on a grid? Should we inject them in a series of reactive zones across a plume to use the natural flow of groundwater to break down that contamination in situ? What configuration do we need to ensure that this has a successful outcome? And often a question that hasn't been thought about is, well, what does success actually look like for that particular site? Are we looking to hit really low targets in a very short period of time? That's going to have an impact on what technologies we choose. Similarly, the opposite end of the scale would be, are we looking at less stringent targets and a much longer cleanup program? Jim is going to be talking about a chlorinated solvent site where we had to reduce really high contaminant levels by something like 90-ish% within 12 months. And that is something that we had to do very quickly. But if we had had 5 years to do that, the cost impact would have been significant. So also, is there this scope for an additional step? So are we able to inform you and help you design a remediation characterization phase? Now, what's pretty typical, as I said, is that somebody would come to us and they've completed a site investigation and now they're looking at different remediation options. What I find delivers often the most successful projects and projects that have a lower cost and higher certainty is if we're able to work together with the incumbent environmental consultant or remediation contractor to do an additional phase of investigation that is focused on helping us and the wider strategy sharpen up the remediation design. There's not only cost savings associated with doing this additional phase of site investigation, there's also time savings as well. And this isn't us saying that a particular consultant has done a bad job. It's just that we're often looking for slightly different things when we're coming up with these remediation options versus if we're just looking to quantify, if you're just looking to quantify risk. So it's just an additional step. It also has a number of benefits. It helps set achievable goals. We're able to look at a site and say, okay, this is what we're able to do in 12 months, this is what we're able to do in 2 years, and we can help everyone set achievable goals and then help all of the stakeholders negotiate that with the regulators. It helps reduce uncertainties, so we can perhaps lower costs and ensure that a particular solution isn't over-engineered or even under-engineered, and it can reduce costs as well, and ultimately speed up that remediation program. So what is it that we need to understand when we're looking at a site and what is it that we need to understand or information we need to gather as part of that remediation site characterization process. Broadly speaking, it can fall into 5 categories. So this may seem obvious, but we need to understand the contaminant and its concentrations so we can define an appropriate treatment technology. We then are looking at the geology and hydrogeology. These things influence contaminant flux. And then we're going to be interested in the site's geochemistry and its microbiology. These things can affect the processes of natural attenuation. And particularly if we're looking to hit quantitative remedial targets, so we've got a number to hit, and if that number is low, chances are we're going to be reaching for some sort of enhanced natural attenuation technique. So I'm going to take you through all of these. So the contaminant type and its distribution. Now, I appreciate many of you, this is going to seem like a very basic and obvious thing that we need to understand. Are we dealing with L-NAPLs? Are we dealing with something that floats on water in the subsurface, so light non-aqueous phase liquids? These are compounds that are typically less dense than water, so they tend to float, and they are often the most common type of L-NAPL that we come across are things like petroleum hydrocarbons, so gasoline, diesel, etc. There are also certain organic solvents that float as well. We also come across DNAPLs, so dense non-aqueous phase liquids, so chlorinated solvents and certain pesticides. But there are also contaminants that sit somewhere in the middle, so that are pretty that neither float or sink. So things like PFAS and things like dissolved phase metals. You know, all of these things have an impact on what ultimately our treatment thickness will be. So how does this impact the design? So I'm a big fan of a sand tank. It's going to be a theme as we move through this presentation. This is a sand tank experiment that was done by the University of Birmingham to illustrate how L-NAPLs move in the subsurface. So what you can see here is someone has released a gasoline, it's then percolated through that unsaturated zone, so through the vadose zone, and then hit the top of the groundwater table, and it starts to spread out. Now, we all know that groundwater isn't static. It moves up and down with the seasons. It might move because of tidal influences, or it could just move due to weather events. And as it moves up and down, it's going to smear a proportion of that contaminant mass across the aquifer horizon. Now, this is important for us. We're going to want to know where this smear zone is because we're going to want to target it with our reagents. It might be that we want to desorb a proportion of that mass so it can be recovered by a pump and treat system, or we may just want to chemically oxidize it. But to understand where this is really important. Similarly, if you weren't using injectable substrates and you were looking at excavation, for example, then this is where a significant proportion of your hazardous waste is going to sit. So if you're looking to do ex situ biopiling, for example, then this is just something to think about. Similarly, then, well, the opposite rather, with DNAPLs, so chlorinated solvents and coal tars, things like this, when they're released into the subsurface, they will start to sink and they'll move through the aquifer matrix. They'll hit an impermeable layer, they'll then pool and then just keep sinking until they hit a aquitard. So it's very difficult to be able to delineate all of this using site investigation techniques. Often what we have to rely on are contaminant concentrations in groundwater. What you're not seeing here is a dissolved phase plume then coming off of this DNAPL. So I would say to you, don't feel disheartened if you can't find evidence of these DNAPLs when you're doing site investigations. Many of you may be familiar with finding coal tars in the subsurface, you know, these black, thick tars, but chlorinated solvents are the opposite. Chlorinated solvents are clear, immersible NAPLs. So this is a CPT cone footage that we had from a site that we worked at with GEA. This is in weathered chalk. And what you can see here, just for scale, these droplets are about 1 centimeter across, are these immersible droplets that you wouldn't necessarily pick up upon if you were taking cores out of the ground. And really, we were only able to see them because we were dealing with weathered chalk. So if you can't find the DNAPL on your site, I would say it's very common. I've worked on perhaps hundreds of chlorinated solvent sites as an example, and I can only think of 5 where they actually found evidence of the DNAPLs. Of course, this is different if you're looking at creosotes and coal tars. Often you can find those, but understanding if the contaminant sinks or floats is important because it's going to influence what we inject where. Geology and hydrogeology is critical as well. So if we look at the superficial geology as an example, the permeability of subsurface soils and sediments primarily influences the contaminant movement and its dispersion. So its reach and the migration of contaminants are going to absolutely be contingent upon the porosity and the interconnectedness of soil particles and void spaces. So where are those flux zones? And also, have we got differentiating permeability? Now, if we do, that's going to have an impact on, are we going to have issues around back diffusion? And also, are we going to have issues around subsurface distribution of injectable substrates? So that heterogeneity is going to affect the delivery of these substrates. So if you look at these 2 graphics here, on the left, you've got a case where we're getting good even distribution of an injectable substrate. So this can result in good radius of influence that both Sarah and Jim are going to touch upon, which may mean that we don't need as many injection points to create good coverage in the subsurface. If we look at this heterogeneous case on the right, where you have substantial variability in the delivery of an injectable substrate, that will likely mean we will need more injection points to ensure that we get that good overlapping coverage. And this, how heterogeneous the subsurface is also going to have a huge impact on whether we think we can hit particular remedial targets. And this is really important when you're looking at remediating chlorinated solvents, where typically we might be looking to reduce concentrations to parts per billion. And if we're looking at remediating PFAS, where we would be looking to remediate sites, we have remedial targets at parts per trillion. Now, why this is important is all because of back diffusion. Now, I don't explain back diffusion particularly well, but about 20 years ago, a sand tank experiment at the University of Colorado was done that does it quite well for me. So what you're going to see in a second is a series of photographs taken over 132 days. What you can see here is a series of clay lenses, so A to D. So these are clay lenses, and then you have sand in the middle. Now, this fluorescein dye is representing dissolved phase TCE, and you can see that it advects through those sand lenses, and then it starts to diffuse into the immobile porosity, into those clay lenses. Now, if we were to just remediate or remove the contamination from the mobile porosity, so from the sands, we would remove a proportion of that contaminant mass, but we've created a concentration gradient. And that concentration gradient means that you get back diffusion. So you can see those tails there on the left-hand side of the screen. And it's that back diffusion that's going to prevent you from reaching those really stringent cleanup goals in the parts per billion range or the parts per trillion range. And injectable substrates can help overcome this problem because they don't only rely on advection, but they can also rely on diffusion into these immobile into this immobile porosity, but it is something we need to know about and design for. So hydrogeology, so this is going to influence flow and transport. We were talking about this in a minute ago. So on sites where we have particularly high permeability, we can rely on treatments that use advection to get transported in the subsurface. So this could be chemical oxidation or chemical reduction, enhanced desorption or absorption. Sites where you have low permeability, so sites where perhaps you have clays. Now, I would say if you think you've got a site with low permeability, but you have a plume, that permeability might be a bit higher than you might be anticipating. But you can use treatments in these sorts of treatments in clay. So you can use treatments that rely on diffusion, like the introduction of electron donors or acceptors that can just diffuse through a porous medium. Where there are challenges, it is where there are treatment challenges, it's where you have contrasting extremes, and this is where you have problems around back diffusion. But these can also be overcome using barriers and etc. Measuring mass flux. So going back to the theme of gap analysis, often this is something that's missing as part of a site investigation. What's very typical is people using slug tests or pumping tests to work out mass flux and permeability, but these methods do not delineate velocity or mass flux, and you don't have really much data resolution. So while we can absolutely use data that you have gathered using pump and slug tests, if you're able to, we would prefer it if there were passive flux meters installed. So in REGENESIS, we do have passive flux meters. So we have something called Flux Tracer. This can identify source zones within high flux areas. It means that we can optimize product placement. And actually, when we're installing things like permeable reactive barriers, we can make sure we're targeting the correct part of the aquifer. It could be that 90% of the flux is moving through 10% of your aquifer. So instead of treating the whole treatment thickness, we might only need to treat a very small amount. If you look at the numbers here, so if you look at the example on the left, we're assuming a mass flux of 20 milligrams per square meter per day. Whereas if you look at where we have installed a hypothetical flux tracer, you can see that we're able to then just target the upper proportion of the aquifer. If you're interested in this, feel free to scan the QR code, or if you just Google REGENESIS Flux Tracer, it'll bring you to the web page where it unpacks these technologies that we have that can be used to measure groundwater velocity, chlorinated solvent plume flux measurements, as well as PFAS as well. Geochemistry is also important, so we're going to drilling down now. So we're going to also be looking at the FOC. We can use this to calculate what we would expect the sorbed mass to be from groundwater data. We're fully sympathetic that site investigation budgets are often squeezed. You'd like to take much more soil samples, but often can't. But so we can use data from the groundwater to back calculate what we think the sorbed mass will be. TOC, equally important, so how much natural organic matter could we be dealing with? This is of interest because this will often be acting as a sponge for contamination and can provide an ongoing source. Again, this problem around back diffusion, and it can also increase electron acceptor demand. So when we're looking to enhance aerobic biodegradation, we're going to want to know about this so we can design for it, so we can overcome this particular demand. It can also have impacts on treatment efficiency for some chemical oxidants as well. Geochemistry, so carrying on, dissolved oxygen, are we going to want to work with the current ambient conditions in the aquifer? Are we dealing with something that is particularly aerobic, so let's enhance that, or do we want to work under anaerobic conditions? You can degrade things like petroleum hydrocarbons under aerobic or anaerobic conditions. One's quicker than the other, but there are ways of optimizing both. Iron and manganese levels, what is the oxidizing or reducing state of the aquifer? And nitrates and sulfates. These things are really important. They're very important when it comes to designing enhanced reductive dechlorination strategies, so treating chlorinated solvents in situ. Often the stoichiometric demand, so the amount of our reagent that we're looking to inject, can be driven by the levels of sulfates in the subsurface, because we're looking to essentially chew through all of those to get to that sweet spot for reductive dechlorination. Similarly, nitrate's important. Nitrate reducing bacteria are very good at degrading benzene under anaerobic conditions. So understanding if we've got lots of nitrate in the subsurface is useful. It's also quite soluble. So if you have a data set and you get a bit of noise, do take a look at your nitrate concentrations. That would indicate that you've had some fresh pulse. Fresh might be a bit of a strong term, but a pulse of water entering your monitoring well, and that might account for why you're seeing a bit of noise. And methane, signs of deeply anaerobic conditions. Microbiology is not always something that we need to look for. Sort of when and where is it important? If there isn't any evidence of biological degradation, then it might be a good idea to go looking for these microbes. For example, if you have a PCE plume and you know the spill is 50 years old and there's no sign of daughter products, then it looks like you might be dealing with a very sterile environment. Similarly, if you have a gasoline plume and you still have a lot of BTEX hanging around and it's 20, 30 years old, not a lot of evidence of weathering, then perhaps look for these microbes. Similarly, if you're treating at depth, sort of the deeper you go, the harder it is for these microbes to get a hold or a footing. So it might be worth looking for them there. If you're dealing with esker formations or extreme subsurface environments of very fast flowing groundwater, this could, there therefore may be a need to look for these microbes. If they're not there, that's not a problem. We can augment them with an inoculum, but we only really want to do that if it's necessary or if we're looking to speed this treatment up. If we've got a natural population, then it can just be as effective to enhance them. Finally, the last part of my last part of my presentation, when should I recommend a bench scale test is often a question I'm asked. And the question I then answer to that question is there something unusual or dangerous about your site's chemistry? So a bench scale test is only really useful if we're dealing with a contaminant that we don't have a lot of experience treating, or if there isn't a lot of literature evidencing that it can be treated using chemical oxidation, absorption, or some sort of bioremediation. So I would say if you're thinking of chemically oxidizing petroleum hydrocarbon contamination, that's a pretty well-trodden path. So a bench scale test often isn't necessary. Similarly, if you are looking to chemically reduce chlorinated solvents, again, this is done very routinely. So a bench scale test really wouldn't be useful. Where a bench scale test can be very useful is on sites where you have an unusual mix of contaminants. So perhaps you have a hydrocarbon plume, but there are some pesticides in there or some pharmaceutical products where we're not sure what the breakdown products of those compounds will be if we do chemical oxidation or if we do aerobic biodegradation. So most of the time, a bench scale test is only useful if there's something unusual or dangerous about your site's chemistry. I would always say do a field scale trial over a bench scale test. Typically, the costs can range from as little as 10,000 euros up to 100,000 if we're doing something quite complicated, because the thing that's probably the thing that's going to be unique about your project is unlikely to be the contaminant. It's more likely to be the site itself. And field scale trials can just tell us so much more information. We can understand the geochemistry of your site and how it reacts when you introduce these injectable substrates. We can understand how the contaminant mixture is impacted. And also we can look at contaminant distribution as well, and ultimately the application feasibility. So it might be that you have a bit of an upfront cost. It might be 10,000 euros, say, when you do this field scale trial, but you might be able to then save that when it comes to the full scale works, because we now have a much better understanding of how just to work on that site. So we can give you a much more accurate and refined cost that's neither over or under engineered. So you often make that money back. So we've evaluated the site, and in this hypothetical situation, we've assumed we think we can help you. we're now moving on to the technology selection and remediation design phase. And it's at this point that I'm going to hand over to my colleague Jim, that's going to talk us through these different processes. So Jim, if you just bear with me, I will make you a presenter. Cool.
How are we looking?
I can see a blank. Yes, I can see a screen now.
Yeah?
Yep.
Thanks, Jack. And hello, everyone. Yeah, I get to talk to you about the exciting bit. Once we have a well-evaluated site, that is, we have reviewed the initial package from the client, the technical and commercial gap analysis has been undertaken, and the treatment goals have been agreed, and any additional stages of remediation design, characterization, investigation work have taken place, we're ready to select the remediation technology and make the treatment design. So where do I start? There are a lot of potential remediation processes and technology solutions to choose from, and this is a good thing. But care needs to be taken that we select the right tools for the job. Our aim is to provide an appropriate solution that is neither under nor over engineered. So to do this, we bring it back to the site evaluation, the remediation design characterization work, and the specific treatment goals. We also need to select an application configuration. Do we need to target all of the contaminant mass in a well-defined source area? And if so, we would reach for a grid application pattern, like this one over here on my left. Are we targeting the plume at the site boundary? And in this case, we're going to be designing a barrier or a series of barriers over on the right of the screen. If the aquifer is particularly fast moving, or we have a very large site, we might exploit groundwater movement in the treatment in an inject and drift pattern. And very occasionally, for example, in a deep bedrock setting or to avoid above or underground obstructions, we can use a recirculation method. So that is, we would apply in one location and we would extract in another to draw the reagents across the formation. And again, we make these decisions in the context of the site evaluation. So to illustrate how technology selection and remediation design works in practice, I'm going to use the example of a large UK site that we've recently worked on. So this is a large chemical works that closed in 2012. Really heavy TCE impact to soil and groundwater from bulk storage and drainage leaks. This is one of, if not the most contaminated site that I've worked on in my career. Really well investigated site, so lots of data for us to inform that site evaluation. And we began remediation work at the site in 2021. So from the site evaluation, the information I have is that we have a very large but well-defined source area and plume area also. The contamination is sitting in a shallow sand and gravel aquifer over impermeable mudstone at around 5 to 6 meters below ground level. And there was an abundance of free and very high levels of TCE in the source area, but we also have a plentiful occurrence of degradation products in the form of DCE and vinyl chloride, and a very large dissolved phase plume of lower concentrations of TCE and a greater proportions of DCE and vinyl chloride. So treatment goals, also pretty well defined from our site evaluation process. So that is, the client wanted 90% reduction in the existing TCE levels at the site within a 12-month period. So quite ambitious given the extent of mass present at the site. It was also important that we avoid a surge in daughter products, and the client really wanted a remediation strategy that could be implemented in a single application so that they could get on with redevelopment of the site. So if I bring this back to Jack's slide at the start of the site evaluation process, this is the information that we needed to know. This is the information that we're seeking in a site evaluation. And post-evaluation for our TCE site, this is the information that we know now. And this is the information that instructs my choice of technology, application, and design dosing. So geology, it's a shallow sand and gravel aquifer. That's going to give me good permeability, so high volume applications are going to be okay here. Hydrogeology, again, that good permeability, so I can expect good in situ distribution of reagents, and the flow regime is well characterized, so I know where to position barriers to protect against any off-site migration. Geochemistry, again, like competing electron acceptors, I've looked at dissolved oxygen, sulfate, nitrate, and nothing looks too concerning here for an enhanced biological remediation approach. This is where we're starting to lead. Microbes, so the presence of TCE daughter products, TCE vinyl chloride, that tells me that the right consortia are present at the site and that reductive dechlorination, biological reductive dechlorination is happening. So again, that supports like leading towards a biological solution, and the need for to bio-augment or to add a consortium of microbes, that's not necessary here. And targets, so 90% reduction TC in 12 months, no daughter product surge, and a single application. So we're looking for something quite aggressive here, something fast acting, but also with enough staying power to not need further applications to finish the job. So what am I going to use? So I'm just looking at the chlorinated solvent technologies here, and there's a few to choose from. So my first option is sorption. So sorption, like our colloidal activated carbon range. So this technology range is not going to be suitable for this site because of the amount of, excuse me, because of the abundance of free phase and dissolved phase mass. It's just too high for our sorption technologies. So we're not going to look at them. So next up, chemical oxidation. So we have Regenox and Persulfox to choose from. We might use those in different scenarios. So those technologies, they can meet really high contaminant concentrations. So yes, that's a tick. But is it long-lived and can it deal with rebound and back diffusing mass? No, it can't. Like for this amount of mass, we would need multiple applications of chemical oxidation. And that will be timely and expensive, and it's not going to meet the remediation goals for the site. Aerobic biological degradation, no, because TCE won't degrade aerobically, or at least not in the time frame that we want it to. So next up is anaerobic biological degradation. Like yes, this is something that is going to work for this site. We know reductive dechlorination is already happening at the site, and we know that we can optimize that with an electron donor. So it's a tick. We'll have that. Let me go back a bit. Right. ISCA, in situ chemical reduction. So this will really accelerate TCE destruction via two pathways, by augmenting further the biological pathway, but also through direct chemical reduction. And it's also going to reduce the generation of daughter products. So again, aligning with our site goals. So tick for that one. And using these technologies together is going to yield a much more accelerated program and increase the likelihood of hitting that 12-month target. So we're going to go for a combination approach here. So I've selected enhanced reductive dechlorination, ERD. So what is ERD? It's the sequential dechlorination of chlorinated ethenes. Here in the video, PCE by a specific group of microbes, and it needs an adequate supply of electrons in the form of dissolved hydrogen to do that. So we can optimize this process by applying a technology that provides an adequate and sustained supply of dissolved hydrogen. So we have a few electron donors on the shelf. We've chosen 3D microemulsion for this site. Why? Because it's 3D, 3 donor. That's a short, medium, and long-term electron donor supply, and it will supply dissolved hydrogen for over 5 years from a single application. So that's going to be really sorry, sticking with that. That's going to be really important for our site because it's going to take reductive dechlorination of a lot of TCE all the way through to ethene, i.e. full mineralization. We can trust this technology that it's going to last from a single application, and we know that's important for the client. And also the emulsion properties of this technology it means it has very good in situ distribution, and that's going to be carried very well in the sands and gravels at this site. I said that we would augment the remediation with in situ chemical reduction using zero valent iron. So ISCA is direct abiotic chemical reduction of mostly PCE and TCE into harmless end products. So that's it's an important feature for this site. We're going to bypass TCE and VC generation, so it's going to really speed up the remediation process and help us hit those remediation goals. REGENESIS' zero valent iron is S-MicroZVI, so S is for sulfidated, and that means there is no passivation by water. It's got really good longevity, so again, no need to top up injections to take this remediation over the line. Micro, it's colloidal in its particle size, so just a few microns across for the particles. That means great in situ distribution, and again, that's going to work very well for the permeability at this site. So I've selected our treatment process, and we've selected our technologies that we're going to use, and now we need to get on with remedial design. So that is dosing, so how much of each technology is going to be adequate for this site, and application, how best to put these technologies in the ground. So remediation design general principles. So first up, we want to define the limits of our treatment. We call that our target treatment zone in REGENESIS speak. So that's the treatment area and the vertical interval. We then want to define the amount of contaminant mass, or target contaminant mass rather, within that treatment zone. We want to start that with representative concentrations. That's really important. We're not just looking at maximums, we're looking at how mass is distributed. We want to look at recent data, and we'd love some seasonal variation. That really helps come up with good designs. Then we will move on to an estimate of the dissolved phase mass. So we will take those represented groundwater concentrations, and we will multiply that by the treatment zone pore water volume to give us an amount of mass in the dissolved phase. Soil phase. Again, we will look for representative soil concentrations that have been taken from the field, and we'll multiply that by the weight, the estimated soil weight of the treatment zone. Where we don't have representative soil concentrations, then we can use carbon water partition coefficients to estimate soil mass from the groundwater concentrations. If it's barriers, we're going to be more concerned with the amount of dissolved phase mass that's going to be intercepted by the barrier over its lifetime. So keeping with our big TCE site, so the target treatment zone is well defined. We have a good idea of the geology of the site. We have good representative concentrations from across the site. So we're in a position to break up the site into zones and determine the amount of the amount of TCE, DCE, vinyl chloride mass in each of those zones. Once we have our estimated contaminant mass, we're going to use a stoichiometric approach to determine how much dissolved hydrogen. Let me go back a bit. To determine how much dissolved hydrogen is going to be needed to reduce that amount of contaminant mass. And we're also going to account for competing sinks. So what else is going to use that dissolved hydrogen? So we're going to look at oxygen, we're going to look at sulfate, we're going to look at nitrate, we're going to look at dissolved metals. And generating an appropriate dose for the site, we're also going to apply a healthy dose of practical wisdom that we've acquired from cleaning up tens of thousands of these kind of sites. Just tricks you learn along the way. So I have my remedial dose. My next decision is what application configuration is going to be best for this site. So our objective here is optimal in situ distribution. Effective coverage in the aquifer we know is going to mean effective treatment and more likely to hit those remediation goals. So a key concept to optimal distribution is radius of influence. So Jack mentioned it. I'll talk about it a bit more here, and Sarah's going to talk about it in the field. So radius of influence, that is the distance at which the injectate can be observed from the injection point. So this video, if I hit play, okay, this video is going to help us illustrate this concept. So when we're in the field, we inject our design dose at, I think, at a number of depths throughout the treatment zone. So to achieve uniform distribution across that target area, we inject. The injection locations are designed to create an overlap for each radius of influence. By interlocking these radius of influences, it ensures all areas receive an effective dose. We calculate a projected radius of influence and injection spacings according to this. And the geology and the applied technology that we've chosen, they all play a role in injection spacing and the injection spacing that we end up upon. Again, to hammer the point home, that good in situ placement and distribution of the reagents is key to the success of the remediation. So a nice tight grid in the source area to ensure that all mass in that zone is cleaned up, and a barrier transect in the plume with really good overlap of our radius of influence from each injection point to ensure integrity of the barrier and interception of all of that plume going through it. So you don't get untreated mass down the other side, and you get nice, clean monitoring wells to the other side of it. Back to my TCE site. So this is the application configuration that we went for. So an ERD and ISCA approach with 3DME and S-MicroZVI in the central source areas where we had a lot of TCE mass. Went for a 4 meter by 4 meter grid spacing, making use of pretty good permeability in the sand and gravels and the really good distribution properties of the technologies that we used to give us confidence that we're going to get overlap of the radius of influence there and really good treatment and effective treatment in the source areas. We supported this with rows with barriers of 3DME only down gradient of those source areas. So in the plume of this site, we knew that there was less mass overall, but there was also less parent compound mass and a higher mix of daughter products in the mix. So ZVI in general, not as effective at treating daughter products, so not considered necessary for the barriers. So again, this brings us back to the point of adequate treatment. We don't want to under or over engineer the design. And this worked really well for the site. We had fantastic results, including hitting that 90% TCE reduction in 12 months and the other targets. If you want to find out more about this site, you can hit that QR code there and it will take you to a more illustrative case study. Why did that site go well? Because it was evaluated really well. We selected the right technologies for the job, and we created a fit-for-purpose remedial design. And finally, it was put in the ground really well. So my colleague Sarah in a moment is going to talk to you about how a bit more about that implementation stage and what happens in the real world. But before she does, I want to introduce another way that we design, and it's for our colloidal activated carbon technologies. And Sarah is going to talk about a case study that uses this approach in her part of the webinar. So the first part of the design process for our colloidal technologies is the same. We will define the target treatment zone and we will estimate the amount of target contaminated mass at the site. But instead of a stoichiometric approach, we're then going to use adsorption isotherms to determine the amount of carbon that we need to put in the ground to achieve a target equilibrium groundwater concentration, i.e. a site target level. So here we are engineering the sorption capacity of the aquifer. These isotherms have been empirically derived for our specific colloidal carbon and a range of contaminants at the REGENESIS laboratory over in San Clemente. And again, we will take account of other contaminants or natural dissolved organic carbon in the aquifer that's going to compete with our target contamination for the carbon. So now over to Sarah to talk about our remediation design and how that meets the real world. So I will stop sharing at this stage and bring Sarah in. Or Jack, are you going to do that?
Yeah, Sarah should be a presenter now.
Okay, thanks, Jim. So as Jim mentioned, I'm now going to talk about how we actually implement the design, and specifically that's the execution and verification of the in situ remedial solution in the field. So I've been working with REGENESIS a few years now, so I'm going to share some lessons learned about how we can achieve success in the field. So firstly, we're going to consider the challenges that the geology, the site structure and usage can present. And the key thing here is that the design isn't written in the stone. And when we're on site, we need to be ready to make changes to ensure that the reagents are applied as desired and that we're getting the correct distribution in the subsurface. We want this strategy to succeed. Secondly, we need to verify injections as we go and be prepared to make changes if the parameters from the design don't produce the desired effect. And this is where our experience of undertaking hundreds of thousands of remediation projects makes a difference, giving us knowledge to adjust. I'm going to talk more on placement verification later. And finally, the whole process is executed through ongoing communication between the office and the field. And I'll share how we manage data in that respect. So I'm going to show two different injection techniques that we use at REGENESIS. First, we're going to look at direct push injection technique. And this utilises a small drilling rig, such as a Dando Terrier or a Comacchio 205, which is ideal for working on construction sites alongside other activities such as piling or in restricted areas such as woodland. The process utilises a hollow stem drill rod, which is fitted with an injection tip, and this has a 600mm retractable screen and a non-return valve on the end. You can see this demonstrated in the video on the left. The rods are driven down to the target depth, the retractable screen is opened and the remediation fluid is pumped through the rods under low pressure. Once the required volume has been applied, the rods are pulled up to the next injection horizon and the process is repeated. And once complete, the rods are removed from the ground and the rig moves to the next position. And critically, no infrastructure is left in the ground with this technique. Now, this application method is typically used in superficial deposits to around 15 meters below ground or less. And frequently, we use direct push technology where possible. And that's because we rely on an extremely extended longevity of our technologies, and often one single injection is sufficient. So it's more cost effective than installing wells. The second injection technique that REGENESIS commonly uses is down the well injection, and this utilises injection wells which are of a similar construction to monitoring wells. A single or double packer is placed inside the well and inflated by water or compressed air to form a seal. And this allows the injection of remedial fluid under pressure into discrete horizons within the well. This method is used primarily in bedrock or superficial deposits which are unsuitable for direct push, or when the remediation design comprises multiple injections of a reagent, such as during chemical oxidation, and where it would be more cost effective to install wells rather than mobilise an injection rig multiple times to the site. So how do we choose our application approach? Well, it's designed based on information provided by the client. So we'll recommend the relevant application technique, either direct push or well injections, and that takes into account the geology, the treatment methodology, access and budget. And one of the key benefits of our technologies is that they're engineered to distribute well in the subsurface by means of their colloidal particle sizes. so they can be injected under low pressures. And this prevents fracturing of the geology to distribute the technology, which would likely occur with non-colloidal products. So the video on the right demonstrates the application of a colloidal product in the near surface and powdered product at depth. And by injecting colloidal products under low pressure, we can achieve good and homogeneous distribution. Now, if we were to inject non-colloidal products under high pressure, you can see how we might observe uneven distribution and fracturing of the subsurface. So not only are you getting a technology which distributes well in the subsurface, it's also easy to inject. So the injectate volumes we design for each injection point also consider site geology to avoid product resurfacing. Now we call that daylighting. Yet considering just all of these factors, it's common that once we arrive on site and start undertaking the works, adjustments will be required in the field due to ground conditions. And the most common issues that we need to resolve are around product daylighting. We can tackle that by either increasing the number of direct push injection points so that we can distribute the injectate volumes further, and that avoids overpressuring the ground, or by reducing the injection pressures of both direct push or well injection techniques to ensure that we don't create preferential pathways either within the subsurface or back to the surface. So as Jim mentioned earlier, ROI is the distance at which the injectate can be observed from the injection point. To achieve uniform distribution laterally across the target area, injection locations are designed to create an overlap of each ROI, seen in the image on the right. By creating interlocking ROI, it ensures that all areas receive an effective dose. And REGENESIS calculates a projected ROI, and that differs by substrate and the volume of the injectate, and that's used to design our injection spacings in grids and barriers. But how do we check that ROI has actually been achieved? Well, we do this through something called placement validation. And this is a validation method to check that those projects have achieved their designed ROI and that the injection points interlock, and that concentrations of the injectate in groundwater are within the optimal range. But how do we do this? What's our method? Well, we'll take a groundwater sample from either a purged monitoring well or a piezometer installed as part of the works. And these are typically located at certain distances from injection points. Normally that's 25, 50, 75 and 100% of the projected radius of influence. And we'll also install piezometers down gradient and at midpoints between the injection points. So I'm going to use our colloidal activated carbon placement validation method as an example for this. So once we've obtained a groundwater sample and recorded parameters such as pH, redox, temperature and dissolved oxygen, the sample is subjected to a colorimetric test whereby it's compared against a known standard to determine the concentration of colloidal activated carbon it contains. The carbon concentrations are based on each specific site, and this enables us to ensure that the designed barrier is completed to the specification. We document all of the groundwater parameters during sampling, as well as the recorded concentration of carbon. And this enables us to have confidence in the barrier and to sign up to providing warranties where they are requested by the client. It also enables us to identify whether there have been any issues with achieving that radius of influence, and therefore if any amendments to the design are needed. I'll talk a little bit more about this in a few slides. So we've spoken a fair bit about the importance of placement validation and how we undertake it and interpret the results. But what about when the results show something we aren't quite happy with? How do we react to those surprises? So, for example, we might have identified a location where the ROI hasn't been achieved, or a point in a barrier where the ROI between two injection points isn't overlapping, essentially creating a gap in the barrier. We have certain standard methods for handling this. So We could, for example, change the volume of water in the injectate mix to further dilute it and aid distribution. We could change the location of those injection points. If we're getting significant daylighting, we may be near an obstruction or a preferential pathway, so we can move away from those. We could also look at changing the grid spacing, such as reducing the spacing between the points and amending the volume of the injectate accordingly. We could change the injection tips, so change the method of injection, meaning the type of tip on the end of a retractable rod, because sometimes distribution can be limited in certain geologies, and we may need to inject through an auger tip or a bulb. And finally, we could change the injection order. So we typically inject each point from the bottom up, and we could swap that around and inject from top. We typically inject bottom up, and we could change to injecting top down. But critically, throughout the site work, the site team and the technical manager work closely together to ensure that we're not impacting the overall efficacy of the design by making these changes. And once we've decided on a way forwards, we can communicate these changes with the client prior to restarting the works, ensuring that there's always full visibility in the works that we do on site. So what about data during and post the injection works? So one of the key factors for our clients upon completion of injection works is access to that injection data. And as such, it's critical that we have a robust data management procedure. During the injection works, we collect a range of data, including the injection pressures, flow rates, injection volumes, a commentary on the works, our placement validation data, and groundwater monitoring. And post-injection works, what's REGENESIS's role? Well, we love to be involved in a project. So once monitoring data becomes available, we will ask for it to be shared with us so we can assist the client in their data review. And we can lean on our placement validation data when we're assessing chemical data that's been provided to us, so that we're able to give a full picture of the site and what's been happening since our injection works. And this allows us to provide recommendations for any further sampling, analysis, or monitoring if we deem it necessary. So I'll move on to a case study now. So to emphasize the importance of data review and management, I'm going to briefly talk about this live site, which is an ongoing project and isn't complete yet. And this is a PFAS remediation demonstration project located on a fire training ground in Sweden. And the site was complex for a number of reasons. So firstly, the geology on the site was challenging because it comprised medium to fine sandy soils overlying a confining clay layer at varying depths. The site also had fast groundwater flow up to around 350 meters per year, and within that a high PFAS mass of up to 200,000 nanograms per litre. So our solution was to install a 70-meter long permeable reactive barrier using our plume stop colloidal activated carbon technology. And the barrier comprised 3 rows of plume stop injection points, and with a row of calcium chloride injection points down gradient. And that was undertaken to prevent the plume stop distributing further than we anticipated with the fast groundwater flow. Works were undertaken by injecting simultaneously with 4 rigs and comprised a total of 188 injection points, completed over a 10-week period. So on a project this complex, it was crucial to employ a robust data management procedure so that we could understand ground conditions during the works and make any amendments as the project progressed. REGENESIS utilises Bentley's Open Ground software, and this enabled us to collect data on rugged tablets in the field using the Open Ground Collector app. I've provided a screenshot of that here. We implemented this because for those of you who've worked on site, you know how badly things can go wrong if you actually lose a notebook. And Open Ground enables real-time data sharing within the project team and development of injection logs or cross-sections upon completion of the injection works. And we can also provide a completion report containing all of this site data. We're also able to produce 3D models of the IPRB that's been installed, shown here where the yellow is the sand just below ground level, black is the plume stop horizon, and orange is that confining clay layer. And this shows that the barrier had absolute continuity throughout the treatment area. However, please note that this shows the injection points only, and it doesn't show the projected distribution, which would create the full radius of influence and those interlocking radius of influence that we were talking about earlier. And by installing 3 rows, we were able to provide sufficient contact time between the barrier and the contamination to ensure consistent absorption. So using placement validation data and our comprehensive data management system I just discussed, we undertake continuous data review as the injection works are being undertaken, so that we're able to identify any potential problems and be reactive to any changes that are required. So in reality, how did this help us on this Swedish PFAS study? Well, during placement validation data analysis, we identified that there was a small section of the barrier around 2 meters long, where our colloidal activated carbon technology was mobilizing down gradient a few meters further than we'd expected. And by identifying this early on, we were able to recommend re-injection of that calcium chloride parking agent to prevent any further transport of the carbon. So what did this mean? Well, early identification enabled a fast response from the site team, and comprehensive placement validation data alongside good data management is critical in ensuring an in situ remedial solution has been successfully implemented on your site. And that's now back to Jack.
Thank you, Sarah. So we are a little bit over time. Hang on, let me just turn my webcam on. We are a bit over time, so we sorry, Sarah, I think we've lost you.
She might just need the camera back on.
Yeah, there we go. Hi everyone, sorry. So we are a bit over time, so we won't be able to answer too many questions, but I have collated a few of them. Sarah, one was on the open ground software, and I'm sort of grouping a couple of them on the open ground software, and also just generally sharing data between the project team. So is that something that's possible using these sorts of techniques? Can you this sort of software, can you share that data between, I guess, Jim and in the office, and then the consultant and other contractors in the field?
Yeah, so within REGENESIS, we were able to share data between site and field. The Open Ground Collector app that we have on our tablets is constantly updated through the cloud. So Jim could look at our data live and we could discuss it whilst I was in Sweden and Jim was back in the UK in our offices. With the wider project group, we're also able to share that data live, and it also provides a data management system, so our clients can also share site data with us through that, so chemical data as well and borehole logging.
No worries. Jim, I've got a question for you on spacing. What were the different spacing approaches used in the grid and barrier treatment for the chlorinated solvent example that you gave?
We use 4x4 spacing in the grid because, again, sand and gravel is good permeability. We went for the same in the barrier. It was 4 meter spacing because, again, same technology, 3DME, kind of that 4 or 5 meters really is as far as we want to push it. We know that we can rely on good in situ distribution with the technologies used here, with 3DME, with ZVI. But we even so, we wouldn't want to be pushing it beyond 4 or 5 meters. That's quite high for a barrier. For other technologies, for the carbon technologies, we want to be a lot closer. So sort of closer to around 2 meters, can be even tighter than that, because you know, there where we are engineering the sorption capacity aquifer, the in situ distribution properties are good, but they're not going to be as good as the micro emulsion. So we want to be a bit closer for a bit more assurance that we're getting that ready to influence overlap.
No worries. Sort of two commercially ones, I suppose. Again, just trying to pull as many together as possible because I'm conscious of time. Sort of questions around, do we need all of this information in order for our products to be considered? We can make assumptions on certain sites, and we'll just be clear about what those assumptions are. Also a question about, can people just buy the products from us? Broadly speaking, yes. So if you don't want us to design, but you do want to use our products just off the shelf, that's something we're happy to do, and the application service is optional. So yeah, I think that's probably all we have time for in terms of this webinar. Again, thank you for sticking with us right through to the end. In the next hour or so, just as a bit of final housekeeping, and you will receive an email with your attendance certificate already attached. And there will also be a link for some feedback on this webinar. The feedback for us is really useful. It helps us improve these webinars that we give, and they're also a really great source of ideas for future webinars that we want to give as well. So if you have any ideas, or even if you'd like to perhaps give a joint webinar with us, please let us know in the feedback form. So thank you, Sarah and Jim, and for all of you online for making the time to listen to us today. I hope you have a great rest of your day. Thanks very much. Cheers. Bye.